My talk will have two parts. In the first part, I'll try to argue how to extend the Atserias-Muller result to bond depth Frege. And in the second part, I'd like to talk about the problem of whether the resolution is weakly automatable. And I'll try to suggest that that problem might not be as hard. So let me start by briefly reviewing the Atserias-Muller result. In particular, let me start with reflection principles. So the reflection principle of a proof system is a CNF formula, this form, expressing the soundness with respect to proofs of a certain size. So the formula SAT says that Y is an assignment that satisfies the formula for X, and the formula F says that Z encodes a period of size S of X. The connection with automatability becomes apparent from the following theorem, saying that there are polynomial time intervals for the reflection principle of P, if and only if there is a proof system of polynomial similar to P, and is automatic. In other words, the canonical pair of a proof system is separated by a polynomial time algorithm, if and only if the system is weakly automated. In particular, if a proof system has feasible interpolation and has short proofs of its reflection principle, then it's weakly automated. This raises the question of whether weak proof system, known to have feasible interpolation, can prove the reflection principle. Atserias and Bonnet show that that's not the case for a solution. They show that the resolution cannot prove its own reflection principle. It's not have short proofs. But once you consider a slightly stronger proof system, namely Res2, then you get short proofs of the reflection principle of resolution. So you can formulate in Res2 the soundness of resolution. So this is how this looks like. You write down these two DNFs that say that Y satisfies all the clauses of Z. So this says that there is an I that is made true by Y. There's a variable that's made true by Y and appears positively in the first clause of C. Or there is a variable that's made false by Y and appears in the first. On the one hand, this says that since it has short proofs of the reflection principle of resolution, if Res2 had feasible interpolation, then resolution would be weakly automated. On the other hand, it gives the basis for this reduction. So given a CNF formula F, we map it to the second part of the reflection principle. If F is satisfiable, then if we plug a satisfying assignment in this Res2 proof I showed you, this becomes true, and these two DNFs become closed. So that becomes a resolution refutation of the second part of the reflection principle. And for the lower bound, we start with a width lower bound. And the way to show width lower bounds, is to find the model in which your formula is satisfied and show that this model is in a certain sense locally isomorphic. So in this case, the model is the brute force resolution refutation of F of size 2 to the n. In a sense, you can fool a prover of limited width into thinking that's what is proving. And once we have a width lower bound, we can turn it into size lower bound using random restrictions. To extend this to Frege systems of higher depth, the first idea is do the same, but for the reflection principles of depth difference. I tried doing that, then I realized it's hard. The second idea is to start with the reflection principle of resolution and substitute variables with depth D subset functions. This is how the first lower bound for bound depth Frege was proved by Frege. When you do this, there are two problems. The first problem is that if you do the substitution in this res2 proof I showed you in an A way, what you get is a depth D plus 1 reputation. And this is off by 1 from what we would want. I claim this you can solve by being careful to get actually a depth D refutation after the substitution. For the lower bound, like in the case of resolution, we want to reduce it to a width lower bound. And when I say width, I don't actually mean width. This couldn't have worked with width because resolution is automated with respect to width. What I mean is index width or block width. So we want a switching lemma for index width. I tried extending, I tried making a hostile switching lemma work for index width, but again, I failed. Then my idea was, okay, why not use what I call the first Sachs-Sipser switching lemma? This will give a much weaker bound, but for the purposes of showing non-automatability, assuming that P is not equal to P, it suffices. It barely works, but it works. So these are the bounds I get. And what's important is that this exponent here is a polynomial of degree d minus 1 in H, and this exponent is a polynomial of degree d in H. So if you pick a large enough H, for large n, this will be much larger than this. So the argument is that if there was an automating algorithm A for depth Frege of running time n to the C, then you could run it for these many steps to the C, and for large n, distinguish between this case and this case. In effect, distinguishing between this case and this case. So solving that.
So I missed what H was, I'm sorry.
Yeah, H just a parameter.
But it doesn't appear in the formula.
H, okay, so H will depend on C. H, I'll choose H.
You choose H.
Yes, and to make this work, H will have to depend on C, on the running time of the, so suppose there is an automating algorithm running in time n to the C, I pick H as a function of C. That's that.
Did you change the formula? Formula different for different H's? The red formula?
No, H does not depend on the formula.
But it must. Does the formula depend on H, the one that you're studying the size and?
Maybe it actually depends on H. Now I can mention it. Yeah, okay, so yes, it depends on H. It depends on H. Okay, so the formula depends on H. So Z here, S here will depend on H. Is that okay? Okay. I'm not too proud about this. The first problem is that it would be nice to have something, to have the reflection principles, or something closer to the reflection principle than what I have. The second problem is that this reduction is to formulas of depth D, which does not preclude the case of depth D Frege being automatable with respect to CNF formulas. So, yeah, so if you could do the reduction to CNF formulas instead, it would be better. A perhaps related problem is whether there are CNF formulas separating, exponentially separating depth D and depth D plus 1 Frege. And it's related because the reflection principles could be a candidate formula for this. Okay, so doing well time. On to the second part. So recall that the problem of whether resolution is weakly automatable is the same as the problem of whether res2 has feasible interpolation. So before telling you why feasible interpolation seems to fail for res2, let me talk about the cases for which it works. And the proofs for which it works are proofs that have the subformula property. So this is such a proof. Every formula is a subformula of the formula that we prove. And I color with red those formulas that are subformulas of the left part of the interpolation formula, and I color with blue those formulas that are subformulas of the right part, of the right side of the interpolation formula. And in the proof DAG, I color a vertex red if the principal formula of the deduction at that vertex is a red formula, and I color it blue otherwise. Now, the problem of computing the interpolant is the same as the problem of determining who has a winning strategy in the following game. So there are two players, Alice and Bob, and they will follow a route to leave path in the proof DAG. In red vertices, Alice's chooses where the two players move to, and in blue vertices, Bob chooses where the two players move to. And when they reach a leaf, one of the players will win depending on what the action at that leaf is. And it's easy to compute who has a winning strategy. So that's a circuit that computes who has a winning strategy. I just replace red vertices with ORs, and I replace blue vertices with ANDs. So this was Greg's interpolation, or Kashmir-Victorson. They're all the same. Now, things go wrong when the subformula is violated. And this already happens in res2. So that's the cut rule in res2. So we have two variables here. And so what happens is that the interpolation problem here gets reduced to new different interpolation problems. And they're different because the shared variables have changed. So the problematic case is when the cut formula contains variables from both sides of the initial interpolation problem. So let's assume that we're in this case. What happens in terms of the game is that both players need to speak. So first Alice speaks, and this gets colored red, and then Bob speaks, and this gets colored blue. But this is a DAG, which means that these two vertices are the same vertex. And in one case, this is colored red, and in the other case, this is colored blue. So the game is the same, but now the colors, the color of a vertex depends on how the two players reach that vertex. I claim we can get something out of this. The first observation is that you can, again, using dynamic programming, find who has a winning strategy. But now at each vertex, you need to store who wins for every possible coloring. and there are 2 to the width of the proof possible models. So bounded width raised to has feasible interpolation. Okay, that's something.
So what is the width of rest?
Right. So in REST2, you have 2 DNFs, right? So the width of a 2 DNF is how many conjunctions are in this 2 DNF.
Sorry, why are you discussing rest2 and interpolation?
Because I want to argue that resolution is not as hard to weakly automate. And this problem is the same as the problem whether REST2 has feasible interpolation. So there's this theorem that says that resolution is weakly automatable if and only if REST2 has feasible interpolation. I mean, whether REST2 has feasible interpolation is is a good problem in itself, but yeah. In particular, is the same problem as whether resolution is weakly automatable, which might be more interesting. I don't know.
Related to depths, like automatability of depths different.
I mean, this is depth 1.
Yeah.
So my idea was that in the first part we showed that depth 3 Frege is hard, and the second part is to show that depth 1 Frege might not be as hard to weakly, not to depth. That resolution might not be as hard to weakly. Resolution is depth 0 Frege or depth 1 Frege. Right? Yeah. Perhaps the 2 parts are not very coherent. So the second observation is what I'm trying to arrive at. My idea was that you can set up the proof in such a way that the colors of vertices only depend on the moves of one of the players. So you can do that by letting Alice always pick first at problematic cards. So if you do that, so given a winning strategy of Alice, in that situation, since colors depend only on her choices, if you given such a strategy, you can verify in polynomial time that that's indeed a winning strategy. So the set where Alice has a winning strategy when she always speaks first in problematic cards, that's an NP set. And you can do the same for Bob. So the situation looks like this. You have 2 languages in NP. One is contained in the complement of the other. And they separate the interpolation pair of REST2 in the sense that one part of the interpolation pair is entirely contained in L1, and the second part of the interpolation pair is entirely contained in L2. To put it in other words, we have 2 disjoint co-NP sets separating the interpolation pair of REST2.
So do you mean L1 and L2 is the interpolation pair?
No, this is the interpolation pair.
Oh, I see, I'm sorry.
A and B is the interpolation pair of REST2.
Ah, okay, and now you've just, okay, fine. I
Yeah.
missed the picture.
Yeah. And so we have 2 disjoint co-NP sets that separate the interpolation pair of REST2. That's a kind of a weak feasible interpolation property of REST2. So the best statement I can make at this point is that resolution is not as hard to weakly automate, assuming this conjecture. That whenever you have this situation, whenever you have 2 languages in NP, the complement of one is contained in the other, and they separate a disjoint pair, in the sense that A is in L1 minus L2 and B is in L2 minus L1, then there's a language that separates A and B and is not very hard to understand. And the best support I have at the moment of this conjecture is that its computability analog is true. So if instead of NP sets, these were recursively enumerable sets, then there is a recursive language separating A and B. So if L1 and L2 were in RE, were recursively enumerable, then that's a set separating A and B. So in the darker region, you have all X's for which the lexicographically smallest certificate for membership in L1 is lexicographically less than the lexicographically smallest certificate for membership in L2. Yeah. I'll try to do something better. But I thought that this is something interesting and I wanted to share it with you. And thank you for. I'll just finish early.
Any questions for the audience?
Yeah, I always time my talk like in a worst case scenario. but I always finish early. So probably I should stop doing that.
I have a question. So
Yeah.
you're saying not so hard to weakly automate?
Yeah.
What do you mean by that? Like,
Okay, my sense. I don't know, I could be totally wrong about this. But my sense is that, so the problem is if you have this situation, find a set that separates A and B, and it's not hard to decide. And given that this is true in the computability world, it makes me think that there is such a set of intermediate difficulties, like a set in NP intersection co-NP or something. But I'm not sure how good of an evidence is that this conjecture is true in the computability world. But I don't know. Okay, so the statement at the moment is that Res2 has visible interpolation, assuming that this conjecture is true. Yeah.
I mean, can I just comment on that? Like, I mean, in computability, like RE intersect co-RE is exactly recursive, right?
Exactly.
So, I mean,
Yeah. Yeah.
This is very close to what you're asking.
yeah, that's what I'm
Yeah.
worried about.
I have a question.
Yeah.
That's two Frege, the same kind of thing would work.
I think so. Yeah. Def2 is like Res2, but the transactions are unbounded, right?
Yes.
Yeah, I think it works also for Def2 Frege.
Now, for higher depth Frege, we suspect that it's not weakly automatable at all because of cryptography, right? So where does it stop? Stops at depth 2? Your intuition.
I don't know. I wanted to ask you about this. So I was not sure about this, and I actually wanted to ask you about this, if this is interesting or if this makes sense, or yeah.
Isn't just this objection that Robert raised, showing that this is unlikely because suppose it is a complement of B, so this is just something which is in the intersection and going B, so you have two sets that are one complement. So the only sets L1, L2 would be the same sets. Then you would then this would just say that you can separate it by something simpler.
But what do you think about this? Do you think that's plausible?
I think it's not possible.
Or it's not plausible?
Because
Because of the special case A is the complement of P.
Yeah.
because it would imply that if you have something in.
No, wait, but if no, you don't have this situation when you take. You're saying take L1 to be A and take L2 to be the complement of A.
Yes, so if you.
No, but
So take a.
But it's not the same, because
It's not the
that,
same. It's definitely not the
if you
same,
do
but
that
it's a
in the
special
computer.
case of what you are asking.
Mhm.
And in this special case, you would get that something that is in NP intersection co-NP actually should have something easier than NP.
Basically, these very strong conjecture seems false. Like it seems like you would need to use the properties system.
Yes,
like,
yes,
automatable theorem,
you need some specifics of where you
Yeah.
came from.
which is
Sure.
fine. I mean, that might be true. but-
Okay, so it's not
Yeah,
as, it's too strong,
Yes.
and you think that it's unlikely to hold.
Well, it's not, it doesn't hold if NP intersects co-NP is not equal to P.
But what if it is equal to?
Well, factoring.
Well, what if NP intersection can be, has always possible number of items?
Not excluded.
Hmm?
Not excluded, but then cryptography would.
In roughly then.
Yeah. No, you probably want to say that A and B should not be arbitrary, but there should be some specifics about it. So it's moral conjecture, it's not formal conjecture.
Mhm.
Any other questions for Theodoros? Okay, well, thanks again.
Thank you.